once we get to a fission, we can now study how we might form asteroid binaries or asteroid pairs following such an event. Now, I should note here when I have this relatively strong statement about all contact binaries spun to fission are initially unstable, I believe this holds for two bodies. Recently, we've analyzed the three-body system, where you have three bodies resting on each other. And there, you can actually have almost all of those systems are also unstable when you initially fission one body. But there's a very small parameter region where you can actually have the system fission into a stable configuration. But it's very small. And actually, at CELMEC, my talk will actually go through that solution in a little more detail. So what happens next after this fission process? Well, this is something that we've been studying using granular mechanics, treating them as celestial mechanics systems, where we can take a pile of self-gravitating bodies, spin them up to a fast enough rate, and then actually track things such as their interior stress and their spin rate in order to determine when they actually separate and enter orbit around each other and what those conditions might be. We're actually able to, it's just the same movie, verify the behavior we see with our granular mechanics models with sort of a continuum mechanics theory as well, and actually show that the sort of shape deformations that these bodies go through are actually very consistent with the theory of how a frictional solid would actually deform. Really coming back to using civil mechanics or civil engineering mechanics type principles. And then by just tweaking the initial component distribution, if you put a little neck in the body somewhere, say, you can really control what sort of initial size ratio or mass ratio the system bifurcates into. So it's actually very sensitive to the initial distribution of the body as well. So it doesn't always, so you can really come up with a variety of different types of fissions and mass ratios between these bodies, just based on our computational mechanics approaches. And actually, we're able to come up with this somewhat complicated chart really describing what happens in terms of the mass ratio between these two bodies, whether it has a large mass ratio or a small mass ratio, and what some of the outcomes of these systems could in fact be. And we'll just step at a high level through some aspects of this, just to give you an understanding or a feeling for how this works. And let's first consider this actually the easier case of if the mass ratio is more equal or greater than 0.2. So in this case, we noted that the free energy was negative, and that we got that from our plot. So there's insufficient energy for these bodies to mutually escape from each other. Especially when we get towards unity in the mass ratio, there's insufficient energy for the two bodies to even do a complete spin relative to each other. So when they separate, they're sort of locked into a, into a librational motion where they cannot even necessarily circulate. You have to have a relatively lower mass ratio in order to get that sort of circulation. And it turns out that that's important too. If there are tides, tides will cause synchronization of both of these bodies. Once they become synchronized, even full or even partially synchronized, there's another non-gravitational effect that can kick in, kind of called binary warp. And just like the Yorp effect, which caused single bodies to spin faster or slower, the binary Yorp effect can actually cause binary asteroids to increase in size, which actually causes them to rotate slower, but causes their angular momentum to increase, or shrink in size, which causes them to orbit faster, but of course decreases their total angular momentum. And when this Bjork effect kicks in, we can have several different, outcomes. They can migrate mutually outwards. They can migrate mutually inwards. They can even form stable relative equilibria. A paper we just had with a postdoc of mine, Alex Golubov, were able to show that these are possible for some outcomes. Here with the movies, you can actually contrast Itokawa, which is very close to that zero energy line. So it has a lot more energy in the system, and you can actually have mutual rotation between both of these bodies. Compare it to something more like Hermes, which has a mass ratio close to 1. And if you look at these bodies, they are ellipsoidal, and you can see a bit of their oscillations. And here, they're really trapped. They actually can't even spin all the way around with respect to the other one, because there's not enough energy in the system. So this is a candidate for settling into a tidally, it is partially tidally locked, and if it dissipates energy, it will be completely tidally locked. And then the binary York effect can cause it to grow or compact. Whereas this one is still much more energetic. So those are interesting, maybe not quite as interesting because they're always stuck to each other. For the smaller mass ratio, where we have this positive energy, it actually turns out that there are several different outcomes that can occur. So first of all, there's sufficient energy for the system to escape. It takes some time because you actually have to, the orbit does not immediately have enough energy to escape. In fact, the initial orbit is a circular orbit. It has to take energy from the rotating bodies and pump it into the orbit to allow it to escape. And that can take some time, months, maybe even years. But it can occur. However, there's also sufficient energy to cause a secondary body to spin so fast during that process that it too can actually fall apart into multiple components. Because if we assume that the whole body is a rubble pile, then these two components that separate from it should be a rubble pile as well. In fact, you saw that in that granular mechanics movie, where we had this huge body, or this one body with a bunch of masses resting on each other. When it split, it was still two collections of bodies. So either one of those spin fast enough, they could split as well. So one of the outcomes that we have is sort of this abrupt or rapid escape. And by abrupt and rapid, I mean within a year or two. So they have total positive energy, and as I just said, energy to escape is drawn from the primary spin rate, because that's the largest repository of energy in the system. And in fact, the larger the mass ratio, the slower the primary spin should be after escape. And in fact, there's a whole that's this mode here. There's actually a whole population of asteroids which exactly fit this sort of a model. And these are the asteroid pairs. And this is taken from Pravik et al.'s Nature paper in 2010. There's some updates to this, but this is good enough for this particular talk. And what they're showing here, or what was shown in the past by Vikruliki and Zvorny, is that there are actually asteroids in the main belt whose orbits, if you integrate them backwards in time, come very close to each other with relatively low speeds. So it's almost like they emanate from a single point in the past. Hundreds of thousands of years. I think they can go up to maybe like 1 million years or so with some level of precision. So the hypothesis is that these two bodies were at one point connected in some sense, and then they separated apart. And in fact, in their initial paper, they had several different hypotheses for what could match it. But with Pravik, Peter Pravik took a number of observations, and they were looking at the relative size and magnitude of these asteroid pairs, and that gives you, in some sense, the mass ratio. If you look at the change in magnitude, you can relate that to a mass ratio or a size ratio. And they also were tracking the spin periods of the larger component of these bodies, of the primary spin period. And if you apply the theory that we just discussed, these asteroid pairs should have a mass ratio that's all less than 0.2, which is roughly this line here. And as you get closer to this limit, the primary spin period should get longer and longer, because it had to give up more and more, relatively speaking, of its energy in order to enable that secondary body to escape. And in fact, that's precisely what you see. So the observation is that the mass ratios and primary spin periods of main belt asteroid pairs match very well with this fission theory. And not only just in one component, but actually matches in these two components, in terms of mass ratio and in terms of the period getting long as you get close to that mass ratio. Since 2010, there have been additional observations, and there are some more interesting outliers that could be special cases, and we actually have a recent paper that just got accepted in Icarus that explores some of these outliers, and there's some other theory that I'm working on as well. But still, the bulk of these guys fit very well with this asteroid pair fission theory. However, we know that we also have binary asteroids, and the ability to form these binary asteroids is sort of called into question because most of the mass ratio of the binary asteroids that we see, not all, but by far most of them, have a mass ratio that's less than that 0.2 that we talked about, which means that when they initially form, they're susceptible to immediately escaping, or escaping after maybe just a year or two, and becoming asteroid pairs. So this was a problem. How do you explain how these binary systems could be formed? And what we realized, which I mentioned already, is that during this period where the system is undergoing this strong dynamical interaction between spins and orbits, it's very common for the smaller body to be spun to a fast enough rate so that it can actually split itself and lose a component, and then you form a three-body system, and then you can actually shed excess energy or absorb excess angular momentum of the binary system, either by ejecting one of the bodies or having one of the bodies fall in the primary. And that actually can act as a stabilizing influence, which can eventually cause the system to settle into perhaps one of the binary asteroids that we see today. So I just have a couple of movies to show this, and we have two situations that we look at here. This is a re-impact case, and here this model shows the actual evolution are these two ellipsoids. However, we seed each ellipsoid with its subsequent shape, depending on mass ratio and the like, so that when this guy spins fast enough, this guy will in fact split into these components. And in this example, it splits and one of them goes back to the surface. It's a relatively low speed impact, on the order of centimeters per second or less. So we don't expect it to be a catastrophic impact. But it does come back to the surface and maybe even distributes itself around the surface. Whereas the second guy actually gets thrown out a little bit and becomes a little bit more stable. And if this process occurs a few times, it can actually stabilize the system. Here's another example where we can have a fission, and here we actually have an explicit point on the surface. And actually, it goes through, this guy spins fast enough to release that particular particle, and we shed some excess energy from the system, which helps to stabilize the system a little bit more as well. And what we were able to show is that through this process, we can actually form binary asteroids, and then other issues such as the binary Yorp effect take over. I'm not going to spend much time on this, but this is an interesting situation where you have a contractive binary Yorp. The tides will always want to expand the system, and you actually can drive this asteroid system into a stable equilibrium. That's actually been confirmed for at least one binary asteroid. And this is interesting because it actually gives us a handle on what some of the internal dissipation parameters of the system could be. So really through this sort of an analysis, we can actually explain many of the different types of asteroids that we see in the population. And again, we're really just applying fundamental approaches of celestial mechanics. So how much more time do I have?
Half an hour. I was signaling for a break.
Yeah. So everyone can stretch for a minute, and we can start up again. Just for a minute. That's all. I don't want to take the full 5 because we have lunch, right? So. Yeah. The dynamics are very nice.
You want me to?
Sure.
So, let's start. No, okay, let's go what?
Okay, so I'm going to go on to the sort of the next part of the diagram. So actually, what we've covered to date, or so far, is actually sort of this upper part of the diagram, where we have fission of relatively large bodies, meaning like larger than 500 meters, and just in terms of the mass ratio that they have, different systems or different processes can act on these bodies, and actually gives us many of the observed binary asteroids or asteroid morphologies and types that we see in the solar system. Now we're going to focus a little bit more on the transition between a larger body and what happens when these bodies become a bit smaller, say around roughly 300, 500 meters in size or smaller. And what this really comes back to, so far we've been thinking about a bunch of rocks resting on each other. They obviously have friction, okay, they're surface forces, and they have gravity because they hold themselves together. But generically, you don't think of them having any other sort of strength. And in fact, it's natural to just assume that these rubble pile bodies are, if you will, cohesionless. And we'll show in a bit that that's not necessarily a good assumption, and in fact, it doesn't fit with what we see in nature. So first of all, I want to touch briefly again on this diagram that we had shown before that shows the spin limit for larger bodies. And it's sort of consistent with the spin deformation limit of spheres of 2 to 3 grams of density. And the simple interpretation of this sort of a plot is that everything to the right is a rubble pile, and everything to the left must be just a monolithic rock because it spins very fast, faster than what you might think of as the fission limit or the spin deformation limit. When you look at it a little bit more closely, the real picture is a little more complicated, just in terms of the shapes, the sizes, the morphologies of some of the bodies that we've seen close up, and even once we really think through the physics that should be occurring for these bodies as well. And one point I just want to make is the fact that we often look, or people often look at this limit as the spin limit, and if you spin any faster than this, the body will just fall apart. Because this is roughly the spin rate at which a pebble on the surface of a body of a density of about 2 or 3 will actually go off into orbit. But that's actually not the way the mechanics works. And in fact, if you look at idealized ellipsoids, this is a ratio of the minimum over the maximum size of an ellipsoid. These are different angles of friction. And this is a normalized spin rate. If you actually increase the spin rate, what you do is you get to a maximum size, depending on the friction. But then as you increase the angular momentum further, or deform the shape further, you actually don't necessarily have a change in the spin rate. And in fact, if you apply some standard failure theories to a body, it shows that once it starts to deform, in general, it changes its shape instead of just spinning faster. And once it changes its shape, it can actually spin at a slower rate, even though the total angular momentum of the system is increasing. This is a theoretical prediction by Holzapfel, something that we simulated in a paper a few years ago. And you can come up with an approximate deformation spin limit, where phi is the internal angle of friction, rho is the density. And what you find is just by controlling the friction angle in the limiting density, you can actually control when that deformation starts. However, once the deformation starts, if you add in additional angular momentum due to the Yorp effect, in fact, the total spin rate of the system can actually go down, just because it's getting a larger and larger moment of inertia. So I wanted to make that point because that's often missed in the discussion, that this is not a spin, it's not a limit at which things disrupt. It's actually a limit at which things start to deform, and in fact, the bodies underneath this line may actually have a larger angular momentum, but they've just started their deformation process. Now, to get back to the main topic, we should go back to our original question again, which is, what is a Rubble pile? And again, it's a size distribution. We know it goes down to microns and up to hundreds of meters across for the case of Eros, say. Itokawa suggested 1/d cubed from centimeters to decameters, and similarly from its sample from microns to hundreds of microns. I don't know if these two size distributions are connected or not, but even for shallower size distributions down to the fines, the finest material, the smallest material, really dominates in number and especially in surface area over the larger grains. And what that means is that all the larger boulders of the body, where all the gravity lies, if you will, should be emplaced or covered in a matrix of finer and finer grains. And the consequences of this are interesting. These fine grains actually serve as a matrix that touch all the other larger blocks. And if you just apply basic properties of cohesive grains as measured on the Earth and the Moon, they actually provide predictions for some very small but non-zero cohesive strength of a rubble pile. Now, let me remind you, everyone here is actually familiar with cohesive grains and non-cohesive grains. If you take sugar, the particles are large enough so it behaves as a cohesionless material. And if you pile, a pile of sugar, it'll just settle into a nice slope. If you stick your finger in there, take it out, it'll sort of fill it in immediately. Flour, on the other hand, is finer than sugar, and it's actually a cohesive powder, and it behaves very differently. If you take flour, you can actually, make a cut and have a very strong cliff. You can stick your finger in flour and have that hole remain. That's because flour is a finer material and it actually has some cohesion. And the cohesion it has is very small, but that's actually sufficient if you take it into the asteroid framework to actually strengthen rubble pile asteroids and allow them to spin faster. So the cohesion or the cohesive strength that I talk about is not the chemical bonds within the rock itself. Those tend to be very strong, megapascals in strength. We see that from meteorites entering the atmosphere. They have to have pressures of megapascals before they, or many kilopascals before they break. What we're really talking about are van der Waals forces. And in microgravity, we've actually shown that these van der Waals forces can supply significant or enough cohesion to actually change the geophysical evolution of these bodies when you spin them rapidly. In fact, for asteroid sizes less than a few kilometers, the van der Waals attraction between gravel-sized grains can become as significant as their weight, and which makes them really more like cohesive powders when these bodies get small enough. We actually tested this idea out and just to see what the geophysical implications of it were with some simple experiments where we took 2 meter-sized boulders and we had some interstitial regolith, finer grains of here, I think, centimeter in size. Everything is self-gravitating, everything is attracting everything else. And the only difference between these two is on the left, we have no cohesion, no van der Waals cohesion modeled at all. And on the right, we have a simple model of van der Waals cohesion, which is published in the physics, and it's a simple one-line equation that I can show you at some point. And then what we do is to see what happens when we add this very little bit of cohesion, is we pull both of these boulders apart, essentially doing a stress test of them. And we want to see how do they react, and can we characterize what the effect of these very weak cohesive forces are. And these movies are timed so that the same force is being applied at the same time. So when I start the movie, the cohesionless body immediately separates, and you see the regolith is left behind and forms a nice ellipsoid, which is what we expect from a self-gravitating body. On the right, however, it separates at a later time, meaning that you need a stronger strength to pull it apart. And when it does break, it actually breaks in a very rough fashion, and the smaller particles preferentially stick to the larger particle, which again is what comes out of an analysis of the simple physics of van der Waals cohesion. So from this, we realize that, yeah, having just a little bit of cohesion in the regolith will certainly strengthen the system. And we've actually gone through a number of simulations and theoretical calculations and determined that if you have a particle size of, say, 5 to 10 microns, which is consistent with what Itokawa found on the surface of, or Hayabusa found on the surface of Itokawa, we get a whopping strength of 30 to 60 pascals. Now, if you know anything about the strength and pressure, 30 to 60 pascals is nothing. I mean, it's hard to even measure that in 1G environment. It's a very, very small force. However, we can, this is what's predicted, and it's actually consistent with the upper lunar regolith, the very highest part of the lunar regolith, where you can have very porous structures because it has very weak cohesive force. So with these measurements, we can actually go back and revise our spin fission theory, our rotational fission theory, and look at it again once we add the effect of cohesion. The way we do this is we apply a Drucker-Prager failure criteria for when there's a plastic deformation of the system. And this is nice because it combines a frictional force with a strength or cohesive force. And it gives us a simple approximate formula for the spin rate at which it will fail as a function of the spin rate at which it will deform, which is mostly driven by the density of the system. And if we plot these spin rates, we see that for various levels of strength, we actually see that as the asteroid size gets smaller and smaller, it has to spin much, much faster in order for the system to actually go through a rotational fission. This first line is if it had a strength of 3 kilopascals, which again is extremely weak. Weak lunar cohesion, 100 pascals, even very weak at 25 pascals, still has a noticeable effect in how fast you have to spin a rubble pile asteroid for it to actually fail and fall apart. So this is an interesting result, and it maybe changes our picture a little bit, that these bodies could still be rubble piles. Maybe these are still rocks. But it also means that there are some additional physics that are going on in these systems. First, I'll go through this very briefly. You can ask, is there any observational evidence for this strength being there? And in fact, there is. 3 bodies in particular have given us estimates of the strength of this cohesive force that could be holding these bodies together. Maybe the most interesting is the asteroid 1950 DA, which spins relatively fast, almost 2 hours. This is interesting. It has a high impact probability, but very far into the future. So we have a good, millennium to worry about this body. And it has a strength of about 60 pascals. It's a large body, so if it hit the Earth, that would be bad. Okay, and it's spinning faster than gravity should hold it together. So if we go there and we hit it with an impactor, we might just break it in two. So it's sort of an interesting challenge. And in fact, we were able to do a stress analysis of the body and actually confirm and come up with slightly more precise estimates of what that cohesion or the cohesive strength of this body has to be, which is in the ballpark of what we estimated. This is 1950 DA right there, a little bit above the 25 Pascal curve, a little bit below the 100 Pascal curve. Another body is the active asteroid 2013 R3, was first thought to be a comet because it had a lot of gas and coma, but actually once it was resolved, they saw it was actually a body that had multiple pieces slowly drifting apart from each other. And we did an analysis based on their observations and actually were able to come up with a range of strengths of a parent body if this were indeed a rotational fission event, between 40 and 200 pascals. And Jewett just published a reanalysis where he narrows down our uncertainties to 50 to 100 pascals. So again, this is another piece of evidence that, yeah, there could be cohesive bodies or these small asteroids could indeed have some level of cohesive strength. The final evidence is 2008 TC3, otherwise known as the Alma-Ata-Sitta meteorites. Here there were pre-entry observations by Scheeres et al. Showing that it was tumbling in a very fast spinning body. However, in our strengths chart, we could show that it only needed 25 pascals of cohesion to actually be a rubble pile and hold together, even with that fast spin rate. Entry observations showed that it had a very large macroporosity and that it was weak, so it had a high altitude breakup, and it had a substantial loss of 1 to 10 micron material in the upper atmosphere. And then the groundfall observations showed that it was a very mineralogically diverse components of this body. The different meteorites from this body were completely different types of asteroids, indicating that the parent body was in some sense a collection or a rubble pile of different components. This one has caveats because we really don't understand what happens when a rubble pile hits the atmosphere at very high altitude. But this is another piece of potential evidence. And here's 2008 TC3 on this chart, seeing that it actually lies below the 25 Pascal line. In fact, there are other tumbling bodies that are spinning close to this line. Now, another way that we can infer the existence of cohesion is also by looking at how the binary asteroids are distributed. And what we find is that there's a statistically significant drop-off in binary asteroids at smaller sizes. And this actually makes sense if there are indeed cohesive forces in these rubble pile bodies. What I have here are at different levels of strength. What you have is for the body to fail, if it were like at cohesive strength of 3 kilopascals, it would have to spin faster than this black line, which is in fact the escape spin limit. If that occurs, the system spins fast enough because there's actually additional forces holding it together, so that when it does finally break, the two bodies are initially in a hyperbolic orbit and immediately escape from each other. Once that process happens, you should stop making binary asteroids, because the binary asteroids that we see are only formed through this otherwise long period of interaction where they may go through multiple spin fissions and the like. That was the only way we could see to reliably form binary asteroids in the population. So as you have cohesion, even at 25 pascals, once you get below a certain size, and here it's at about 300–400 meters in diameter, you see that when it does split, the bodies have to be spinning so fast that they should immediately escape from each other. And this actually gives us this additional pathway for what happens to rubble pile asteroids in the solar system. And you can think of it almost as a fork in the road, where if the size is bigger than a certain size, the spin rate is such that the system forms an initially bound binary and goes through a very complex evolutionary process. When the body gets below a certain size, the failure spin rate is greater than the escape spin rate. There's an immediate escape, and the bodies will tumble once they escape. We'll talk about that in a second. You can actually assume conservation of mass, come up with a very simple way to relate the size of a subsequent body in terms of the number of components it splits into and the initial body size and how many splitting events it goes through. So if you think about it, if you have a fast rotating body that assumedly is in uniform rotation, and if it splits, and if these two guys escape immediately, they should both be tumbling. That's because the spin rate is conserved across the split, but the total angular momenta are not necessarily aligned with this body anymore because of the the principal axes of these bodies are certainly not conserved across the split. So that initially this body will actually be in a tumbling motion immediately upon when it splits. And then if you look at time frames for these guys to settle down into uniform rotation, they tend to be short relative to the York time scale. And in fact, we see that some of these very fast spinning tumbling bodies, here I'm only showing the tumbling bodies, are actually near this cohesive strength spin limit. So it's a little more evidence for what's going on. Once this process happens, you have a larger body, it gets spun up, it splits into components. These guys maybe immediately escape from each other. They start off at a high spin rate. They can be further accelerated due to the York effect. They have to spin even faster before they spin again. And you can actually come up with an expression that approximately captures what the change in spin rate should be for this new fractured body to actually achieve its own fission spin limit and break into additional components. And in fact, if you compute the time between these fractions, you actually get a power series that converges very nicely, and it gives us a finite time for once a body gets small enough and it starts going through this new splitting process, and the time to which it takes for it to be completely disaggregated into its component rocks. Now, the individual rocks that can constitute a rubble pile asteroid can spin extremely fast before they would fail, because they have strengths on the order of many kilo to megapascals. But the process of disaggregating the rubble pile into these component rocks only takes a finite amount of time. Right now, the estimates of this time are very rough, because this is the paper that does this calculation was just published this year, and we're still trying to refine some of the uncertainty in a number of these parameters. But it's certainly it can be as short as 400,000 years for a rubble pile body to actually disaggregate into its smallest components, or if we want to be very conservative, it could be several million years. So this is a little bit of discussion about caveats related to that, but that's more for a planetary science community. So in terms of these cohesive forces, we're able to show that rubble pile asteroids can be strengthened by cohesive forces, and this strength comes really from the smallest grains in their size distribution. The simulation and the theoretical predictions that we get are consistent with the measured strength of the upper lunar regolith, which is also a very fine powdery material. And if we fit it to the population, it gives us an estimate of 25 to 100 pascals. That's consistent with the mean grain size of 2 to 8 microns for a lunar type regolith, and that roughly agrees with the Itokawa measurements. And then also there have been these recent observations that are also consistent with the same level of strength as seen for these rubble pile bodies. So in some ways this completes that final chart or that final branch in that larger evolutionary diagram that I had showed earlier. So how much time do I have? I'm about done,
12
right?
minutes.
What?
12 minutes.
Oh, 12 minutes? Oh, okay.
That's it.
Okay. So maybe this cohesion theory is the most controversial part of this whole theory that we've laid out, just because we're suddenly adding in new physics into the system. However, there are some additional opportunities to test this theory coming up with the Hayabusa 2 and the OSIRIS-REx mission. First of all, we'll be able to study the sample return of these missions and to see what these unprocessed asteroid material properties are. See if we can measure the fundamental mineralogical cohesive strength of these bodies, or some specific parameters that need to be measured. In addition, the Hayabusa 2 mission has an impact experiment that enables direct measurement of the regolith strength. And for OSIRIS-REx, we will accurately track the spacecraft, and it will enable us to have insight into the internal density inhomogeneities, and we'll be able to test different theories of strength and morphology that directly relate to some of the predictions from this cohesive strength theory. In particular, Hayabusa 2 will actually form a crater on the body, and depending on how large the crater is, you can actually directly relate that to what the cohesive strength of the regolith of that body is. So that's one experiment that we'll be able to do to actually test how strong the surface of the regolith is. And then again on OSIRIS-REx, depending on what the surface morphology looks like, we're able to distinguish whether it should have a strong or a weak core, and this directly relates to how the cohesion is distributed through the body, which again will tie back to this basic theory. So we're very much looking forward to these two missions to the asteroids to give us a better insight into what goes on there. So I guess I'm a little early, but still I can summarize what finishing up in this last part, and for this talk today. What I can conclude, I think, is that the celestial mechanics of rubble pile asteroids, really these rotating collections of rigid bodies resting on each other, when appropriately applied, can explain and predict many phenomena observed in the asteroid population. As you go through this, we actually find many interesting questions that, that need to be answered for this process to be better understood. And they're really interesting and open questions about how systems with coupled orbital and rotational motion dynamically evolve. And especially, I think what's interesting here is how the tidal theories can be applied to these highly dynamic environments where we have large changes in spin rates and proximity and tidal forces over very short time periods. So I think that's a very interesting topic, in addition to many other more dynamically focused or oriented topics. And another interesting conclusion is it seems that the size of the smallest grains in these rubble pile asteroids seems to matter a lot. And in fact, it's an interesting point where it provides an intersection between the classical physics of gravitating bodies and sort of a quantum physics, where you have the van der Waals forces and these other sort of molecular level forces that become involved. And then to finish up, I'll just show this diagram again, where we've been able to, at least at a simple level, start to explain all the different sorts of asteroids that we see in the population. Although, again, there's certainly a lot more work that needs to be done to have a better understanding and a better fleshing out of this entire theory. So, thanks for your attention today, and I'd be happy to take some questions.
Yes, the two numerical experiments that you showed with and without cohesion, where you had those big pieces and the small grains or regolith. So I was wondering how the cohesion of the small grains could act on the two big bodies. Are they enveloping also? Is there a thin?
No. And in fact, if you look at the theory for sort of the surface contact forces, van der Waals forces, it's actually the geometric mean of the two radii of the body. The force is proportional to that.
Mm-hmm.
So the larger the bodies, the larger the radii, the stronger the force.
Yeah.
So actually, the cohesive force between a small grain and a large body is greater than between two small grains. So that's why then they stick to the large boulders. Yeah.
That's a big question.
Yeah.
What do you think are typical maximum boulder sizes of these intact pieces in units of the overall mass, for example? And would this maybe influence the results in some extreme cases at least, you know?
Yeah, well, so if you look at the size population, there are some interesting, rather large bodies, and there's actually a few more now. This is a relatively old chart that seem to be spinning very fast. And this guy is pretty crazy. It's like 300 meters in size, spinning at a rate of less than 1 hour period. And indeed, this could be evidence for what that maximum size of the intact boulders could be. Also, for the near mission to Eros, some of the boulders that we're seeing lying on the surface of that body were on the order of a few hundreds of meters. So there won't be as many of those from a classical size distribution. For every one of those, you should have 1,000 that are 10 times smaller. So that whole size distribution, that could be an indication. And there are planetary scientists who study, what the likely fracture pattern of a large monolithic block is once you hit it, and you get 1 over d cubed size distributions in general. So if you apply that to a large enough, proto-planetary body, you could potentially get very large components. So yeah, the size distribution should dominate everything.
So one of the pictures of Itokawa you showed us show that it has kind of a head and a body, and that was a Rubble pile asteroid. So I remember that a lot of the pictures of Comet Churyumov-Gerasimenko
was even more extreme. Yes.
Yeah, it also was like a head and a body. So, but that's a comet. Are comets also occasionally Rubble piles?
Yeah, a little bit different because you got ices in the center, so the components can actually be quite strong. But actually, we did an analysis of Comet 67P, which actually was published in Nature last year, where we were able to apply similar sorts of approaches and theories to analyze some large cracks that were seen on the surface of the body. And by doing a stress analysis of that body, we were able to show that this comet was spinning faster in the past. It had some other interesting implications. But we're also able to come up with estimates for the cohesive strength between those two components. And they turned out to be on the order of 60 to 100 pascals again. So I think with cometary bodies, what you may have is the different cores might be a little bit stronger because they have ices in the center. But what's Comet 67P looks like is two different cores that actually seem to be resting on each other. So yeah, that's the same theory can be applied, although there may be a little bit different aspects to it.
I think there is a question for me.
Firstly, thanks for your contribution. And my question is like, how about the influence of the Sun, the Mars, and the Earth, their gravity, and how about the Sun radiation on the evolution of the asteroids? Because if we are discuss the period of millions of years, I think maybe their influence have some.
The gravitational influence? Yeah, that can have some influence. And in fact, initially it was thought that close flybys of planets would cause the binary asteroids to form. But further analysis of that idea showed that it's actually more effective in destroying binary asteroids than creating binary asteroids. But yeah, planetary flybys should have some influence as well. They are not as common as the sunlight. So the orb effect hits everything, whereas only occasionally will you have a close flyby of a body to a planet. However, those close flybys can be very important too, and sort of reset the system in some sense.
It's almost time, so let's go. English question? And we, so this one.
If I show some three cases of asteroids where you could measure the cohesive strength in order to verify the theory.
Yeah.
Do you know how is the process of measuring this information from these asteroids?
Well, yeah, for each one of them, it's not a direct measurement, but it's more, the theory predicts this, and, or using the theory, we can infer it should have a certain level of strength. And if we applied the theory and the level of strength was very inconsistent with our theory, then that would block our theory. If it's consistent, it doesn't prove the theory, but it's consistent with it. So it's not so much that it's been measured and proven to be true, but it certainly has been shown to be consistent with the overall theory that we've been developing. So it motivates us to continue to look for additional places to measure this.
I think that one of the main importances of hypothetical sampling return, right?
Well, in our opinion, yeah. Everyone else is now. They're more interested in the early chemistry of the solar system, which has more fundamental, information about life and all that. We're just doing this little study on the side, but we're interested.
Okay, so now it's time, so let's thank Professor Scheeres again for his lecture.